basically what we learned in chapter 6 is that air is constantly moving. Air tries to balance out. So air flows from higher pressure to lower pressure. So with air flowing to higher pressure to lower pressure, the winds start to curve into low pressure in a counterclockwise fashion, convergence at the surface. You remember back in chapter 4 where we talked about convection. When you heat the atmosphere, air will rise. And what happens is, as air rises, you get convergence at the surface. So where do you find the most heat on the Earth? Well, when we talked about chapter 2, the heating of the Earth, there's a surplus around the equator. So the equator gets very, very hot, and that's where you start to see low pressure starting to rise. So around the globe, you're going to have different circulations, and that's one of the things that we're going to be looking at as we go through chapter 7. What's the wind flow in the United States? What's the wind flow near the North Pole? What's the wind flow near the equator? What's the wind flow near Florida, or what we say 30 degrees north? What's the wind flow at 90 degrees north? What's the wind flow at 60 degrees north? So we want to understand the wind flow around the globe. So chapter 7 is about circulation of the atmosphere, right here, circulation of the atmosphere. And overall, there's different scales to this weather patterns. So when we look at the global scale, we're talking about major storm systems circumventing the globe that will move from Asia around into the Pacific Ocean, into the United States, back out to the Atlantic Ocean, into Europe, and so forth and so on. Think of around the globe. And part of that scale, or planetary scale, okay, those are long waves in the westerlies. So we're talking about constant moving of air over several thousand miles, constant moving around the globe. So our scales of motion that we're going to be looking at, they're categorized by their size and their lifespan. Are they constantly moving, that they're around for weeks and months and years, or are they around for a short period of time, that they're here for maybe 10 seconds, or they're here for an hour and then they're gone? So there's different scales and different time frames that we're going to be looking at as far as the air moves. So remember, chapter 6, air pressure and winds, how is the air moving? So we're looking at low pressures and high pressures. Winds move in a certain direction thanks to those three forces. Remember the pressure gradient force, Coriolis force, and friction. Those three forces change the wind at the surface. All right, so let's talk about these scales of motion. One is macro scale or planetary scale. Those are long waves in the westerly. They last for a long time. Then we have synoptic scale, which is a weather map. Think about the United States. We're talking about 2,000, 3,000, 4,000 miles, and this is going to include cyclones and anticyclones, or as you now know, high pressure and low pressure. Then we're going to be looking at mesoscale. Mesoscale is much smaller. We're looking at thunderstorms, tornadoes, land and sea breezes. Now we're talking over a much shorter geographic distance, and we're also looking at a much shorter time frame. So for example, a thunderstorm. Most thunderstorms last an hour, 2 hours, maybe 4 hours tops. And they cover maybe 10 miles, 100 miles, 300 miles. So a much smaller scale moving with thunderstorms. Same thing with tornadoes. And think of the sea breeze on Long Island. Winds come in off the Atlantic Ocean, it cools down the South Shore, and then air starts to rise. So these are much smaller scales compared to our planetary scale and synoptic scale. Then we have microscale. Microscale is our smallest scale, and that small scale covers a very small geographic location or distance and also a time frame. So one example would be a wind gust. Remember, if you're walking outside, all of a sudden the wind picks up. It doesn't stay that way for hours and hours and hours. A wind gust, a little bit of turbulence, would last maybe 15 minutes, 20 minutes, 30 minutes. Maybe you're walking across Farmingdale State College around campus. You see the trees move very briefly, and then it's over. So those are microscale, very small time frame, very small geographic location. Mesoscale, by the way, mesocyclone, that is also an indication of a very intense rotation. It's an indication of a possible tornado. So mesoscale, thunderstorms, tornadoes, land and sea breezes. Mesocyclone could be the formation of a tornado. So those are the scales of motion that we're going to be looking at. So this is the diagram from our book. And you can see on the left-hand side, it talks about the lifespan, and on the bottom, it talks about what the actual scale is. So again, microscale, a wind gust, a microburst, or a dust devil. A dust devil is a very quick movement of air that kind of pulls up the dirt along the ground and kind of moves things around. Very different from a tornado, where a tornado will pull air up, but at a much stronger strength. So days to weeks, hours to days, minutes to hours, seconds to minutes. That is our lifespan. Our scale, microscale, mesoscale. Then we get into synoptic scale and planetary scale. And you can see macro scale goes up to more than 40 to 50,000 miles. So you can see thunderstorms and tornado, that's on that mesoscale, minutes to hours. Wind gusts, microscale, microburst, that can come out of a thunderstorm. So very small, very intense, and only around for a very short period of time. Hurricanes, anticyclones, so high pressures and low pressures, they can be around days to week. That would be under our synoptic scale. And then long waves in the westerly, trade winds. We're going to talk about the trade winds in just a moment. So these are much longer scales, meaning that they're going to cover a much longer geographic distance, and also they're going to be around for a much longer time, as you can see, days to weeks. So westerlies in the atmosphere, they constantly move around the entire globe, covering 30, 40 to 50,000 miles. So this is our lifespan versus our scale. And this is the exact diagram from your book in chapter 7, so you can get an idea of those scales. Now, we're constantly looking at air moving, and air can constantly move all over the place, up and down. That's what chapter 4 was talking about. How do we get air to go up and down? And a difference in pressure will cause wind. That's what we learned in chapter 6. So when you have a difference in pressure, higher pressure and lower pressure, you can get these different types of mesoscale or microscale winds. And here's an example of a valley breeze, where you have the cool air sinking and then the warm air rising along the mountains. And at night you would have the opposite, where you get the warm air rising in the center of the mountain range here. This is the valley. And then the cold air kind of sinks off the mountain. So this is just one example that we could look at the smaller scale of our winds. So as we take a look, going back at our wind scales and what happens, and the sea breeze is also a part of that mesoscale, where you get winds coming in off the water. You have a difference in pressure. Out over the ocean, you have high pressure, converging air, and this is convergence right here. The land heats up very fast. You get convection, air rises, and with that, the air wants to fill a void. So that's why you get the wind off the water coming in over land. This is the sea breeze. Air is stable out over the ocean. Land air masses heat up very rapidly. You get convection, air rises, and you get convergence, where the wind flows from higher pressure out over the water to lower pressure over land. And you can kind of see this cycle on this diagram, where the wind flows from the ocean out over land, rises, and if you have enough convection, you get clouds. And if you remember, if you've ever visited to Florida, you get a lot of heating during the afternoon and a lot of afternoon thunderstorms. That's a stronger sea breeze compared to Long Island. A lot of times Long Island, we just get the clouds building, and most of the time you'll see them developing right along the LIE. That's where the convection of the center island would be. That's where we get the rising air. So sea breeze is on that mesoscale time slot, and this can be around for minutes to hours, and you get the cooler air coming in off the ocean. So Jones Beach, Robert Moses, the South Shore could have temperatures in the 70s, but places near the LIE, Dix Hills, Plainview, Syosset could be in the 80s to around 90 degrees. So that is our sea breeze, where the air flows from the ocean into the land. As the air is heated up faster over the land, you get converging air from the ocean. All right, so in chapter 7, we're constantly watching air moving, circulation of the atmosphere. You can see the different diagrams here of that sea breeze. So one of the things I want to look at is the global perspective, what's happening around the globe. This is one of the diagrams, and also as you take a look at in your study by chapter, you will also see this as well. So this is from your Pearson. So if you go into chapter 7, you could look into the smart figures of global circulation. You can look at the e-text, and this is that same diagram, and you can play this diagram and kind of see where the air is moving and how the air is moving as well. And you can see right here on this diagram that there's different names around the globe. And that's one of the things that we're going to be looking at. Each wind flow has a different name. and we can get an idea of what the weather may be because of that wind flow in different portions of the globe. All right, so let me get rid of some of these maps here. So going back to our global circulation, if you look at pages 195 to about 202, you're going to see all these different diagrams in the book, and also you can look at the e-text through the Pearson study guide as well. So one of the things I want you to notice is that notice along the equator, we have these red arrows. That's warm air moving in. So at the equator, we get a lot of incoming solar radiation. Remember chapter 2, a lot of incoming solar radiation. So as the air is heated at the ground very rapidly, it becomes very buoyant. So that air rises at the equator. So now you have convergence. So converging air into the equator, warm air moving into the equator, and that air is rising. So this is part of what we call the Hadley Cell. A scientist many years ago figured out, hey, air flows from high pressure to low pressure. Where is low pressure? Where is high pressure? And this cell only dealt with right around 30 degrees north to the equator. So you can see the red arrows indicate warm air. The blue arrows represent colder air. So you have warm air rising at the equator. And remember from chapter 6, converging air at the surface, diverging air aloft. So this is where we have low pressure at the equator. So converging air at the surface, diverging air aloft. So as that air is diverging outward, it's going to be sinking, okay, and converging into higher pressure and then going down to the ground and spreading out again. So we have low pressure at the equator and we have higher pressure, okay, at 30 degrees north. This is what we would call our subtropical high. So at 30 degrees north, we have diverging air at the surface. It is converging into the equator. So along the equator, we have several different signifiers for low pressure. One area, this is called the Equatorial Low. At the equator, you have low. This band here near the equator, we have what we call the Intertropical Convergence Zone. Intertropical Convergence Zone. Intertropical convergence. Remember, convergence, air is coming together near the equator. Now, this air mass will fluctuate throughout the year thanks to, remember from chapter 2, where the sun's direct rays are hitting. So during our summer, this equatorial low, intertropical convergence zone, the doldrums, moves a little further north during our summer. It gets closer to around 10 degrees north, and then it goes a little bit further south during our winter. So this will move with fluctuation during the seasons. Where's the warmest air? The sun's direct rays hitting, and then where it moves throughout the year. So at the equator, you have the equatorial low, doldrums, and the intertropical convergence zone. Now, you have converging air from high pressure at 30 degrees north. This is called the northeast trade winds. Here's your trade winds, wind flowing out of high pressure into low pressure, out of high pressure into low pressure. So the northeast trade winds, okay, are the winds coming out of high pressure converging into this low pressure. And the reason why it's called the northeast winds, because the winds are coming from the northeast. Remember, wind flow around high pressure is clockwise. So when you have high pressure at 30 degrees north, it's clockwise. You get one direction in the United States and a different direction as you get near the equator. So from 30 degrees north to the equator, that is the northeast trade winds, and the wind is flowing out of high pressure into low pressure. 30 degrees north, again, which is called the subtropical high, clockwise wind flow in the United States. See these red arrows? That is called the westerlies. The winds blowing in the United States from the west to the east, from the west to the east of the United States. So our storm systems come from the Pacific Ocean generally into California, Oregon, and Washington and move eastward. Now, they don't always move in a direct line, but the general track as they're flowing is moving west to east in the United States. So from 30 degrees north to 60 degrees north, that is what we call the wind flow, the westerly. So this map is showing circulation or wind flow around the entire globe. So let's do a little bit of a recap. The equatorial low, doldrums, or the intertropical convergence zone is formed from the converging air where the northeast trade winds meet south of the equator. These are the southeast trade winds. High pressure down around 30 degrees south, High pressure flows counterclockwise. There's a different wind flow south of the equator. So you have the southeast trade winds meeting the northeast trade winds. That is the intertropical convergence zone. That's where the equatorial low is. That is also where the doldrums is. At 30 degrees north, we have the subtropical high pressure wind flowing clockwise here. Now also at the North Pole, you have very cold air. That's where high pressure is. So you have high pressure at the North Pole, high pressure at 30 degrees north, and at 60 degrees north, we have low pressure. So take a look at this globally now. At 90 degrees north, or the North Pole, wind is flowing outward. Cold, dense air is sinking down to the ground and spreading out. So at 90 degrees north, we have the polar high. At 60 degrees north, we have the polar front. We have converging air. These polar easterlies are the wind flow coming out of high pressure. So out of the high pressure, out of the North Pole, you have the polar easterlies. The high pressure, near the subtropical high, you have the northeast trade winds. And then to the north of that, you have the westerlies. So where the polar easterlies are meeting the polar westerlies, we get the subpolar low and the polar front. So along 60 degrees north, we get the polar low, okay, or the polar front and the subpolar low. Converging air at around 60 degrees north, converging air at the equator, diverging air, this is all at the surface, diverging air at the North Pole, and 30 degrees north and 30 degrees south. So notice the blue arrows, that's cold air, the red arrows, warm air. So you have air constantly rising, converging and diverging. So let's look at this again. At the North Pole, you have the polar high. Wind flows outward at the surface, you get polar easterlies. At the surface, you get air converging at 60 degrees north, which is the subpolar low or the polar front. In the United States, from 30 degrees north to 60 degrees north, you are looking at the westerlies. Along 30 degrees north, we have what we call the subtropical high. From 30 degrees north to the equator, you have the northeast trade winds. At the equator, you have the equatorial low, doldrums, and also the intertropical convergence zones. And down near 30 degrees south, you also have the subtropical high. But from 30 degrees south towards the equator, you have a wind flow called the southeast trade winds. So you have a lot of different winds and global circulation. Remember, wind flows from high pressure to low pressure, high pressure to low pressure. So the other thing here is, see along 30 degrees north, you have something called the horse latitudes. Well, way back when, the 1400s, 1300s, 1500s, when you had sailors coming in from Portugal and Spain, from Europe, trying to come into the United States, well, right along 30 degrees north, you have high pressure. High pressure tends to have lighter winds than lower pressure. So when you had sailboats coming in from Portugal and Spain and Europe, as they were going through high pressure, there wasn't much wind to fill the sails to move the boats. So they had to make the ships lighter. They had men who rowed the boats, okay, and they had the sails, but if you didn't have support of the wind moving the sails, it was very difficult also to row the boat. So to get a sailboat to move, you need to make it lighter. And one of the things they did was they threw the horses overboard. Horses weigh a lot, okay? They could weigh 200, 300, 400, 500 pounds. They either ate them or they threw them overboard so their boats could move to get to the New World, or what we now know, the United States or the Caribbean. So that's why around 30 degrees north, where we have high pressure, you generally have light winds. That's why this is called the horse latitudes, is because when the sailors from Europe came over to what is now known as the United States and the Caribbean, they didn't have much wind. They had to make their boats lighter. They threw the horses overboard. I know it sounds kind of weird, but 30 degrees north, where the subtropical high is, that's also typically where you have the lighter winds. So generally where you have convergence, you have stronger winds. Where you have divergence, you have weaker winds. One of the things I want you to also remember from chapter 2, the sun's direct rays move from the equator to 23.5 degrees north, which is the Tropic of Cancer, to 23.5 degrees south, which is the Tropic of Capricorn. So as the sun's direct rays continue to move, these wind flows overall will move. So for example, in the United States summer, this subtropical high will move a little further to the north, so we tend to get much warmer air. In our winter, December, January, February, that polar high tends to move south, which means this polar front tends to move south. So all that cold air to the north tends to move south. So our air mass comes from Canada in our winter. Our air mass generally comes from the Atlantic Ocean and the Gulf of Mexico in our summer. So we get different wind flows throughout the year. So again, look through pages 195 to page 203. You'll get an idea of this wind flow and this globe. So again, understanding the terminology, understanding what the wind flow is, and the naming convention. At 90 degrees north, you have the polar high. From 90 degrees north to 60 degrees north, you have the polar easterlies. Along 60 degrees north, you have what we call the polar front or the subpolar low. That's where we have convergence. In the United States, we have the wind flow called the westerlies, where storms move from west to east. And we get that westerly wind from the subtropical high, which is located around 30 degrees north. And then we have the northeast trade winds from 30 degrees north to the equator. The equatorial low, low pressure, air is rising at the equator. So as these air movements around the globe constantly move, you can get different type of weather throughout the year. So let's look back at the graphics here. I have numerous graphics to give you an idea of where you have high pressure and low pressure. This is just another one of them where you have high pressure at the North Pole, low pressure near 60 degrees north, high pressure at 30 degrees north, low pressure at the equator, high pressure at 30 degrees south, and then so forth going down, low pressure at 60 degrees south, and high pressure at 90 degrees south. So you can have constant moving of air around the globe. So with that constant movement of air, you're getting different weather features. So this is one of the diagrams that is also in an e-textbook on Pearson and also your physical textbook. So one of the things I want you to notice, at the North Pole where it's very, very cold, you get sparse precipitation all year long. It's not too cold to snow at the North Pole, it's too dry. High pressure, sinking air. You don't get air rising, you don't get condensation, you don't get precipitation. So high pressure, sinking air at the North Pole, you get very little precipitation. Notice around 60 degrees north, subpolar low, the polar front. That's converging air. So air is rising, you get condensation, precipitation. Long Island is located roughly around 42 degrees north, 40 to 42 degrees north. Subpolar low, ample precipitation in all seasons. So we can get heavy rain in November, heavy snow in January, heavy rain in April, March, June, August, September. We have the chance of seeing ample precipitation all year long. Now we still get our droughts and our dry spells, but at any given month, we have a chance of getting wet weather because of the subpolar low and the polar front. We have convergence near Long Island in the United States, near Canada. We get rising air condensation precipitation. Now, once you're around the subtropical high, since it fluctuates a little bit during the seasons, you get some seasons that are dry, some seasons that are wet. And along the equator, you get ample precipitation all year long. Again, where low pressure is. Where you have low pressure, you're going to get moisture. Where you have high pressure, you tend to have less moisture. So this is giving us an idea of what type of moisture we would have in the area. So again, going through chapter 7, looking at these notes, understanding global circulation. And again, this global circulation will fluctuate throughout the year. Here's the intertropical convergence zone. Remember, the northeast trade winds meeting the southeast trade winds. By the way, this is the prime wind belt for hurricanes. Southeast trade winds meet the northeast trade winds, intertropical convergence zone. Notice where it says January and July. So notice it fluctuates a little bit around the globe. As we go into the northern hemisphere summer, the intertropical convergence zone moves north. As we go into the winter in the northern hemisphere, the intertropical convergence zone moves south. So low pressure and high pressures are constantly moving as incoming solar radiation changes throughout the year, where the sun's direct rays are hitting throughout the year as well. So again, understanding how the wind flows. Now at the surface, we have friction. Remember, friction slows down the wind and the speed. The Coriolis force in the northern hemisphere deflects the wind to the right, and the pressure gradient force pushes the wind from high pressure to low pressure. PGF, pressure gradient force, wind flows from high pressure to low pressure. In the United States, wind flows from the west to the east. Now, some of you may have heard of the jet stream. The jet stream is above the ground. It's roughly about 30,000 feet above the ground. Now, that high up, there's no friction. The jet stream is going to be much faster than the winds at the ground. The jet stream is also going to separate those polar easterly winds to your westerly warm winds. So as it fluctuates throughout the year, the jet stream is a wave in the atmosphere. It'll fluctuate throughout the year. It'll push warm and cold air to different places. So let's look at this map here. Here's the jet stream, this green arrow. Cold air to the north, warm air to the south. In the winter, you have a bigger difference in pressure. Very high cold pressure up towards Canada, low pressure down near the equator. The bigger the difference in pressure, the stronger the winds you're going to have. So for example, in January, Minnesota could be 15 degrees below zero. Miami could be 75 degrees. So you're talking 80, 90 to almost 100 degree temperature difference in the winter. So that's going to lead to a difference in pressure. That's going to lead to stronger winds. So the polar jet stream is stronger in the winter. Now, in the summer, the jet stream is much weaker. That's because you don't have a big difference in temperature. Remember, a bigger difference in temperature will lead to difference in pressure. That'll lead to difference in stronger or lighter winds. So in the summer, it could be 85 degrees in Minnesota, which is over northern United States, and it could be 85 degrees in Miami. So there's not much of a temperature difference there. Or it could be, 75 degrees in northern North Dakota, and it could be 90 degrees in Miami. So not a big temperature difference, not a big pressure difference, hence why the jet stream winds are weaker in the summer and stronger in the winter. And the jet stream winds are also going to separate the cold air and the warm air. So what we're going to be looking at, this is a diagram from your book. This is kind of what the jet stream looks like. Remember, the winds are much stronger above the ground. The jet stream winds tend to flow west to east in the United States. They're much stronger. They could be as high as 400 miles per hour above the ground. There's no friction at 30,000 feet to slow down the wind. The reason why we don't have 400 mile an hour winds at the ground, friction. It slows down the wind at the ground. So here's your jet stream. The cold air will be to the north. The warm air will be to the south. Notice how there's little waves. That's because high pressure and low pressure will be constantly moving and the wind will flow like little ripples. So cold air to the north of the jet stream, warm air to the south. And what you can see here is that if you were to have a little bit of a cold outbreak, you would hear the meteorologists on TV or wherever else that there may be a little dip in the jet stream. So that allows cold air to come out of Canada into the United States, and you can see that warm air. So there's a constant flow of cold air and warm air around the globe. So that's why it's very important to understand where we have these higher pressures and lower pressures. So one of the things we're going to look at here, the upper level winds, or what you'll notice where it says flow aloft here, flow aloft. That's above the ground. This is the jet stream. It's roughly about 30,000 feet. Now at the ground, you can see high pressure and low pressure. Remember from chapter 6, go back and look at the diagrams. Where do we have converging air at the surface and diverging air aloft? Converging air at the surface, diverging air aloft. That's with low pressure. So you see this red L down here at the surface? Cyclonic wind flow, which is counterclockwise at the surface. Wind is flowing inward. It is rising and diverging aloft. So this is how we get these little ripples, what we call ridges and troughs in the atmosphere. Troughs are associated with lower pressure and bad weather, ridge associated with higher pressure and good weather. So take a look at this. Where you have converging air at the surface, you have rising air. Rising air leads to clouds and precipitation. And from chapter 5, depending on how cold the air is, it could be snow or sleet. So rising air will lead to clouds and precipitation. So where you have rising air, you're going to have unsettled weather or bad weather. Where you have sinking air over higher pressure, here's your anticyclonic wind flow or diverging air at the surface. That's where we're going to get sunny weather conditions. Lighter winds with higher pressure, stronger winds with lower pressure. Then above the ground, we have these little dips and ridges. So where we have these ridges above the ground, they tend to bring the colder air down to the ground. So where we have this little trough, that brings in cold air to the ground. Where we have ahead of these troughs, that's bringing warm air from the ground upward. So there's a constant movement of warm air upward, cold air downward. So what meteorologists can look at, where we have air constantly going up and down, we can get an idea of where these storms are. Again, these are all diagrams in your book and also in the Pearson E textbook that we could be looking at. So where we have low pressure, notice you have warm air rising. That'll bring warm air upward. You can get clouds and precipitation. Warm air rising. Cold air sinking. Cold advection behind low pressure. Warm air ahead, cold air behind. This is where you have a trough developing near low pressure and you have a ridge near higher pressure. So again, troughs are with low pressure, ridges are higher pressure. Ridges tend to have good weather, okay? And depending on where you are, if you're on one side, you'll have cold air advection. If you're on the other side, you'll have warm air advection. So always constantly taking a look at that wind flow. So just to recap, okay? Low pressure, convergence at the surface, rises, divergence aloft. Higher pressure has convergence aloft, air sinks or substance, air goes down, hits the ground, and then divergence out. And this air is constantly moving around the atmosphere. That's where we're looking at different things in the atmosphere to kind of go over. So again, the jet stream is going to be faster in the winter, slower in the summer. The jet stream will separate warm air and cold air. Also, you have ridges and troughs with the jet stream and the movement of that air, wind flowing around higher pressure and lower pressure. And in our global circulation, understanding the wind flow. What is it called at a certain location around the globe? And when you have these wind flows throughout the, most of the year, these are called the prevailing winds. So in the United States, for Long Island, our prevailing wind is generally more from a westerly direction. That's why our weather here on Long Island is different than the weather out towards Seattle or Washington. Notice the red arrow here. Their wind flow is majorly off the Pacific Ocean. There's a cold ocean current there, so they tend to have more low clouds and moisture. As opposed to us on the East Coast, our wind comes in off the land more often. That's why we tend to be more dry than Seattle, Washington. So I hope you can appreciate that point, that the wind flow in the United States, west to east, brings moisture to the West Coast, and then it dries out a little bit along the East Coast. But if our wind was ever to change, our weather would be much similar to Seattle's weather. So again, understanding the major concepts here of Chapter 7. Understanding the circulation of the atmosphere. What are the winds called at certain areas around the globe? The scales of motion. Microscale, mesoscale, okay? Planetary scale, synoptic scale. Synoptic scale weather maps. That's one of the things that we look at, synoptic scale weather maps. By the way, these are synoptic scale weather maps where you have high pressures and low pressures. Those are synoptic scale weather maps that we can see what's going on. These weather maps are synoptic scale weather maps. They show high pressures, low pressures, and they show wind flow around systems due to the isobars. So a lot of different things that are going on there. So again, in Chapter 7, understanding the global circulation. One of the things you want to look at, pages 195 to page 205. That'll go over more of this global circulation. So again, you can see near 90 degrees north, that's the polar high, all the way down towards the southeast trade winds, which is at 30 degrees south. So make sure you understand those wind flows. And understand precipitation, where we're going to get the most types of precipitation throughout the year. Near 60 degrees north, near 40 degrees north where we are, we're going to get ample precipitation throughout the year. So that's my class notes. Please read through Chapter 7.